So in this next lesson, what we need to do is start to talk about descriptive statistics. And so we have statistics is broken into really two groups, descriptive and inferential statistics. In descriptive, we start doing all the calculations and organizing our data, etc. And so we're going to get into the idea of frequency tables, frequency distributions, graphs, etc., in ways of organizing our data here in this lesson. So we'll start jumping back to chapter 1, section 1.3, frequency tables and levels of measurement, and then we'll jump more into distributions in chapter 2. One thing to understand is rounding and how rounding is going to affect your calculations. So we have general rounding rules depending on what we're doing, but the most basic rounding rule that we usually work with is essentially to carry your final answer one more decimal place than is present in your original data set. When you round, okay, you should only round your final answer, because when you round in intermediate steps of a calculation, what happens is every time you round, you introduce error into your answer. And the more times you round, the more that error is compounded. So what happens is if you keep rounding throughout your calculations, your final answer can be thrown off by quite a bit. So we don't want to round in the intermediate steps, if possible. Now, if you're going to, and you have to round in the intermediate steps, carry more decimal places than you know you're going to need, okay? So if we know how many we're going to need in the final answer, because we're going to carry one more decimal place than our original data set, then when we're doing rounding in intermediates, what we're going to do is we're going to carry at least twice as many decimal places as we know we're going to need. So the error can be as small as possible, and it won't throw off our final answer at all, or even very much, okay? But make sure you try not to round as much as possible. And there are different ways we can do this, and we'll see this as we go through calculations. But you're gonna hear me say this a lot about rounding. Do not round until you get to the final answer. So anyway, let's talk about frequencies and frequency tables. So the idea of a frequency table is it's a way of organizing your data by grouping data by the number of times the data occurs. So here's an example of 20 students were asked how many hours they work per day. And these were all the different data values. So one was 5, one was 6, one was 3, okay, and it was all measured in hours, right? And so when you look at all these numbers just sitting here as your data values, you don't get a whole lot necessarily out of that. So we want to start organizing it, and the way we do this is a frequency table. So we can list each hour that someone worked here, and we would call these our classes of our frequency table. Sometimes the classes consist of just one value. Sometimes they consist of a range of values. And then we would list the frequency, or the number of times each one of those data values occurred here in the frequency side. And this starts to help you organize what's happening. And just by looking at this chart, we can see that most people worked 5 hours, and 3 hours was the next most. Kind of was pretty spread out. You know, most of it's kind of in the middle, a little less on the ends. But you start to get an idea of what your data looks like in a frequency table like this. So it's just a way to organize your data. We could take that frequency table, we can then convert it into what we call a relative frequency table, which converts it into decimal versions of a percent. So it's sort of the part over the whole, and it tells you how many times something occurred relative to the entire group, and that's why they call it the relative frequency table. So while 3 people worked 2 hours, okay, you want to see how that compares to the entire data set. If we convert it to a relative frequency, well, there were 20 people in our data set total. If you add up all your frequencies, it tells you how many students you sampled. And if we divide that 3 by 20, okay, or turn it into a decimal, 0.15, that tells you the relative frequency. You can leave it as a decimal, but oftentimes you'll also see that written as a percent. So if you multiply that by 100, you'll then see it written as a percent, and that's 15%. Okay? And this one would be 25%, and 15%, and 30%, and 10%, and 5%. And when you look at it as percents instead of decimals, I think it's easier for students to read, or just general public to read, relative frequency table and percent in terms of what it means. So I could say 25% of my students worked 3 hours. 30% of my students worked 5 hours. And it's still giving you the same information here. The most was right here, 30%. The second most was right here, 25%. But by looking at the percent, you're seeing is how do each one of these frequencies relate to the entire set. And that's called a relative frequency. So you could do a frequency table, you could do a relative frequency table. Again, you just divide the individual frequency by the sum of all the frequencies. If you wanted to turn into a percent, you would then multiply by 100. We could also do a cumulative frequency. A cumulative frequency is when you continually add up your relative frequencies. Okay? So we could do it two ways. You could do a cumulative relative frequency or just a cumulative frequency. So a cumulative frequency, we would just continue to add up each one of these. What I'm going to do is I'm going to put a little column right here. I'm going to call this the cumulative frequency, in which case you add up your continued frequencies. So 3, this would then be 8. I keep adding. The next one, I add another 3, which is this frequency, to this one, and I'm going to get 11. Then I add this to this one, which gives me 17. Add this to this one, which is going to give me 19. Add this, I get 20. And the purpose why we would do this is we say, all right, 11 people worked 4 or less hours. Okay? 19 people worked 6 or less hours. So you're adding up your frequencies as you go to sort of see how many worked that amount or less, how many fit that data value or up. All right? We could do it with the relative frequencies as well, which is what this column is doing, in which case, your relative frequency for the first one is 15%, and then you add that to the next one, which is 25%, to the cumulative relative frequency. Then add the next one to that, you get this. Add the next one to that, you get this, etc. And you should get all the way up to your 100%. Again, it's decimals, it's not percent, it would be just 1, but if you multiply everything by 100, you get to your 100%. And so, sort of the same reason. You could do it with the relative or regular frequencies, but the cumulative, the whole approach is to add up your frequencies as you go to figure out how many data values fit that class or less. So here's another table where we talk about heights in inches of soccer players. Okay, we did 100 male soccer players, and they looked at their heights. Now, there's so many heights there that instead of listing each height individually here in the first column, they list a range of heights. Okay? And this is your class. So your class now fits a range of heights. Each one of these classes should be exactly the same width. The width is the size from side to side of this class. And so you want each one to be the same width so it's not dispersed unevenly. And then you say, okay, well, how many fit into the first class? Well, 5 soccer players were heights in this first class between 59.95 and 61.95. 3 fell into this next class, 15 fell into this class, and you can get your frequencies. And what you see is most of your soccer players kind of sit right here in the middle within these couple of classes here in the middle. You can convert each one of those values to a relative frequency. Since there was 100 players, you would take each one of these numbers and divide by 100. Okay, 5 by 100, 3 by 100, and you get your relative frequency. If you want to look at it as decimals, you can. If you want to look at it as percent, you would say 5%, 3%, 15%, etc. Okay? And that would be your relative frequencies. If you want to do cumulative relative frequencies, you would just add up all these relative frequencies as you go, and you continue to add. 5%, 3% gives you the 8%. Add another 15% on that, you get 23%. Add another 40, you get 63%, etc. You could do it just with the frequencies themselves and add up So we could say 5, and then we'll get to 8 because you add 3 to that, then 15 to that would give you what, 23, then 40 to that would give you 63, etc. And these could just be your cumulative frequencies. So you could do it just with the frequencies, or you could do it with the relative frequencies, but the cumulative you continue to add up. So again, just another frequency table, but it helps you organize your data so you can really understand what's happening with our data value. If I just showed you the actual height, 100 height of soccer players, you would just be looking at 100 data values sitting on a piece of paper. And I don't know that that would really get you a whole lot of information just staring at 100 heights. But once you start organizing it in a table like this, you can really start to understand what is happening with your data values. All right, so then we start looking at organizing a little bit more. We're going to do stem and leaf graphs, we're going to do line graphs, we're going to do bar graphs. So it's essentially just ways of taking some of the information we've already looked at with frequency tables and the number of times data values occur, etc., organizing it more in a graphical fashion than in just a table fashion, but same general purpose, okay, is to understand what's happening with our data. A fairly simple way to plot out your data or graph your data, other than the frequency table, is something called a stem and leaf graph or a stem and leaf plot. Okay, it's called both of those things. And it's a way of organizing your data into groups, similar to what the frequency table does. We do it in a slightly different way, where we break each data value into two parts, the stem part and the leaf part. And the leaf consists of the last significant digit of the data value, and the stem is everything else. And so you see here, this is how you would break it down into your stem and leaf. I sort of split it down the middle, and the idea here is that this number right here is 33, and this number right here is really three different numbers, so it's 42, 49, and 49. And so the idea is you have 40s in this group, 50s in this group, etc. And this is the second digit, the last digit of each one. So if we look at a couple of numbers and think about how we split them up, 23 would be split into a stem of 2 and a leaf of 3. So we're going to split it like this. 432 would be a 4 and a 3 for the stem and a 2 for the leaf. 5,432 would be 5, 4, 3 for the stem and 2 for the leaf. And a 9.3, same idea, 9 for the stem, 3 for the leaf. And this is why it would be important that when we do write this, we do it in smallest to largest, so we can identify which numbers have decimal points, etc., based off of the data values. And we could see the difference between the last significant digit being a 0.3, so a 3/10, or 3 ones, etc. So here's an example of Susan Dean's spring pre-calculus class. The scores on the first exam are as follows, and they're ranged from smallest to largest. So you see we have 33, so 3 is the stem, 3 is the leaf. Then we have a bunch of 40s, so 42, 49, and 49. So we're going to split that into 4 as the stem, and then 2 is the leaf, 9 is the leaf, and another 9 is the leaf. So this is actually 3 different data values right here. But it's representing the data values that are in the 40s, and then the 50s, the 60s, the 70s, etc. So here you can see we have a lot of values in the 60s. We have a lot of values in the 90s. Okay, so we can sort of see where most of our data values fall. We can see where they fall relative to everything else. And similar to what we had in the frequency table, but really you can see the actual data values here rather than how many data values you have. And that's the big difference with the stem and leaf plot or stem and leaf graph versus the frequency table. Here's another one. If we're looking at distances in kilometers from home to, say, a supermarket. So they asked a bunch of students or people, and they found out, okay, let's let's see what we have here. We have 1.1 kilometers, 1.5 kilometers. It's already in order, and we want to make a stem and leaf graph. Then what we want to do is we want to answer this question. Do the data values seem to be concentrated at certain values? Okay, so if we create our stem and leaf graph, you see we get 1.1, 1.5, that's what this represents here, those two, 2.3, 2.5, and 2.7, okay? And then we can keep going. We see we have none in this range here, okay? So there are no data values in those. And by the fact that we have nothing there tells us, all right, well, then the next group would then be 12.3, so 12 is the stem, 3 is the leaf. Clearly, most of our data values are clumping up right about here. So we do have a concentration of values right there in the 3.2 to 4.8 range. I would say that's where most people have their distances from the supermarket. And you can clearly see that 12.3 is what we would call an outlier. Okay, it's pretty far away from all the other data values. There's this gap here that has no data values, and then you have this one random data value. So someone lives really far away from the supermarket comparative to most other people that are right here in this range. We could also do something called a line graph. Line graph is much easier to do in a frequency table. If we have a frequency table already created, we have our different classes here, whether it's a single value or it's a class of values, same general idea. We could say, all right, if this represents the number of times a teenager has to be reminded to do his or her chores, 0, 1, 2, 3, 4, 5, and how many times that happened in each case. We can then convert this to a line graph where this scale represents the number of times, this scale represents the frequency, the dot represents what's happening in each class. So 0 times, that happened twice, 1 time, that happened about 5, 2 times, that happened 8, etc. And then we can create a line graph that kind of gives us a nice picture of what this frequency table is doing. Another way to visualize your data is with bar graphs. I'm sure we've all seen bar graphs before. Again, with a frequency table, these work out very, very well in creating the bar graph. Essentially, each class is represented by a bar. And so, if we look at something like this, where this is 2011, Facebook had 146 million users in the United States, and we're looking at the different age groups and how many users they had. So if we think about, this first one was age 13 to 25, had 65 million users, 26 to 44, 53. And then we could also look at it as its percentage for thinking about maybe relative frequency here. And then 45 to 64, 27 million. And so we could easily take this and convert this into a bar chart where the first bar would represent 13 to 25, the next bar would represent the 26 to 44, etc. And then the height of the bar would just be the frequency. Now, in this case, they chose to do the height to be as the percentage or the proportion. This is the relative frequency here. Proportion, relative frequency. We'll talk more about proportion as we get through the semester, but it's all the same thing. They chose to use that as this scale, but whether they use the relative frequency or the frequency as the vertical scale, the chart shouldn't look any different because these are just converting this number here to the percent, relating it to the whole. But anyway, you see most were in this group, the next most were in this group, and the next most are in this group. Probably today, I would guess, this was in 2011, I would guess if they did it today, it would probably have the reverse picture. I would say probably 45 to 64 would be the biggest group here, and then it would trail off maybe the other way. I don't know a whole lot of 13 and 25s are into Facebook anymore, but whatever. So anyway, the bar chart. Line chart, bar chart, they're all basically going to do the same thing. They're going to help you visualize what's happening with your data. And if you have a frequency table already created, it makes it real easy to create these charts. Pie charts work really well if you're working with percents. If you're working with raw data numbers, it's not as easy to do a pie chart, but if you're working with percents, it makes making a pie chart much easier. So here is a standard diet. If you're looking at people who eat processed foods, animal products, etc., and you had the percentages for each one of those, you would be easily able to put it into a pie, knowing that half the pie is 50, so if it's 55, you kind of just estimate it. Usually we don't get too exact with these pieces of the pie. I mean, you can measure the angle and find out that this would be 30%, this would be 55%, and you can get these pie pieces exact. But usually when you're creating a pie chart, you just try to make it roughly close to where it should be. And then again, helps you visualize the data so you clearly see processed food wins here in terms of, you know, the standard American diet, unfortunately, and animal products is number 2. It would be nice if this category right here was number 1 and this category was number 2, but clearly it's not in this chart. But anyway, again, visualizing your data. Pie chart, another way to do it, but the key with pie chart, percents, okay? You really should have everything as percent, so your relative frequencies would be really what you would want to use in order to do a pie chart. Where if you did a line chart or a bar chart, it kind of doesn't matter which one you use. Pie chart, definitely, percents is the way to go. In this next section, 2.2, we're talking histograms, frequency polygons, time series graphs. This is basically all the same stuff we just talked about. A histogram is a bar chart. A frequency polygon is a line chart. Time series graph, more of the same. So really this section is just more of what we've already talked about in a little bit more detail. We'll talk about how you can create a histogram more specifically in terms of the widths of the classes, etc. But really this is all the same stuff. So here this definition I think maybe gets a little bit too complicated, but a histogram consists of contiguous joining boxes, essentially bars, has a horizontal and vertical axis. The horizontal axis would represent your class, the vertical axis would represent your frequencies. Again, you know, horizontal is your data. You could do your vertical as frequency or relative frequency. It really doesn't necessarily matter which one you use. The graph should really look the same either way. It really is going to give you an idea of what the shape of your data is, a picture of what's happening with your information. We'll also be able to talk a little bit about the center of your data and how your data spreads and the variation of your data. And that's really going to be the next lesson we're going to get into, but you can start to see that in your histogram. You really want to make sure that you use a histogram when your data values are fairly high. If you only have like 2 or 3 data values, it's a little hard to create a histogram. So we look at trying saying maybe 100 values or more would be good to create a histogram for. It's not a hard rule that it has to be 100, but just histograms, bar charts, they don't work out well when you have a very limited amount of data. So creating a histogram is much like creating a frequency distribution in that you want to decide how many bars you're going to have, which would be your classes, and then you want to decide, you know, where your starting point's going to be, and then you want to start divvying up your data accordingly. So things that we would do to create a frequency table would be all the same things we would do to create a histogram. And typically what you would do is you would create the frequency table first using the methods we're going to talk about, and that would help you organize the work, and then you would use that to then create the histogram. So as far as the number of bars you want, number of classes you want, 5 to 15 is typical, what you would see. You know, anything less than 5 usually is probably not enough, especially if you're dealing with a large amount of data. Anything more than 15 is kind of overkill. It's too much to look at. It's too busy. It doesn't organize your data concisely enough, okay? One thing you want to do with a lot of this is you want to try and make things as easy as possible. So you want to make sure that your class widths are manageable, that your starting point is lower than your first data value. That seems like common sense, but you want to make sure you get your first data value into the first class. And you want to try and limit the amount of fairly complicated calculations you have to do to create this. So you want to create a histogram fairly quickly. One thing that can be helpful is that when you're creating your classes and your starting point is to look at the number of decimal places you have in your data values and to start at a location that's one decimal place more than your data values. And this will ensure that no data value will fall in between two classes. And so, like, let's say, 6.1 is a data value, and that had the most decimal places of any of your data values, and it's also the smallest data value. Well, we would like to essentially use two decimal places to ensure that we could get this data value in the first class, and all the other data values won't fall in between classes. So think of having maybe a starting point of 6.05. That's got two decimal places, so we just happen to subtract 0.05 off. It's really random, but 0.05 off. But that will allow us, if we start there, that will allow us to ensure that this first data value is in the first class. And by having two decimal places as our starting point, all the other classes will start at two decimal places. And it'll ensure that none of our data values fall, say, in between two classes. Or let's say our data value that has the most decimal places is 2.23. And let's say the lowest data value happens to be 1.5 though. But this had two decimal places in it. So we want our first class to fit this data value in, but we also want it to have three decimal places. So a good option would be maybe to have your first starting point to be 1.495. That's got three decimal places, but this first one falls right after that data value. Again, it just, from a calculation standpoint, it helps. And more examples all the same. Let's say you have a 3 decimal place data value that has the most decimal places. So maybe you want 4 decimal places as your starting point. Your lowest data value happens to be 1, so we want to go just below that. So let's say maybe 0.9995. That would be a good place to start. You don't have to start there. We could start at 0.9999, but we wanted to have 4 decimal places because this one has 3. But starting at a 5 as the last one is easier. A 0 or a 5 here would be easier because we're going to continually add up our widths to generate our class boundaries. And so, 5s and 0s are good starting points there. So let's say we have all these data values. Okay, look at all these data values here. These are heights in inches to the closest half inch of 100 male semi-professional soccer players. And so it's 100 data values here. And if you're looking at all of them, they all have values between 60, which is the lowest, and 74, which is the highest. And the most decimal places would be 1 decimal place because it's to the half inch, so 0.5. So we look at all this and we decide, okay, let's start putting this into a histogram. Really a frequency table that we're going to convert into a histogram. So since 60 is our smallest data value and 1 decimal place is the biggest number of decimals in any of the data, we're going to go with, say, 2 decimal places. We can go 3, 4, 5 decimal places, but it's kind of overkill. So let's go just below 60, and let's carry 2 decimal places. So let's say 59.95. That's where we're going to start, okay? That's better than, say, starting at 61.5 because that would be a problem. This wouldn't fit in there. We won't want to go over it. We could start at 60, right? That would be fine too. But here it says, okay, let's start at 59.95. There's no hard rule to how we're supposed to do this. There's just some good procedures we could follow that could help us with not having as many problems as possible as we go through. And so make sure your first data value falls into your first class, and make sure none of your other data values fall in the cracks between classes. And so this is why we're doing what we're doing. Again, here's your data values. Biggest one is 60, our smallest one is 60, biggest one is 74. So we really want to kind of go from 59.95, and let's go all the way to bigger than this, so 74.05 should be kind of the spread that we're going to go through. All right. So next we're going to have to figure out what's the width going to be for each one of our bars. Okay, what kind of width do we want for our bars? Well, that's really going to depend on how many bars we want altogether. And so you remember 5 to 15, pick a number, it doesn't really matter. You can decide around what your width should be. And so let's just say we wanted 8 bars. Okay, let's say we wanted 8 bars, random. I could have said 7, I could have said 10, I could have said 5. Let's say 8. So to figure out what the width of each bar should be, what we want to do is we want to take that bigger number that we want to go up to, and that smaller number we want to start at, take the difference between them and divide by the number of bars we want. In this case, 1.76. 1.76 is going to be the width of each bar. Okay? So we were going to take that and we're going to say 1.76. Well, that's going to be kind of hard to keep adding 1.76 over and over again to get all our widths, because 1.76 for the first width, 1.76 for the second width, etc. So what we'll do to make it easier on ourselves, let's just round it. Let's round it up to 2. So if we round this up to 2, okay, then we could say, all right, we're going to start and we're going to add 2 over and over again. We're going to get all our widths. So if we start with the first boundary, 59.95, and we add 2 to that, that's much easier than adding 1.76, which is why we just rounded it to make it easier on ourselves. So round it up to 2. We're going to say 61.95 should be the next boundary. And then I'm going to take that, I'm going to add 2 to that, 63.95 would be the next one. Add 2 to that, 65.95, etc. And if you look, what that is the boundaries for the first bar, and then the second bar, and then the third bar. One thing that's usually a defining characteristic of a histogram as opposed to just a regular old bar chart is that the bars are right up against each other. Okay, there's no space in there. The bar chart we saw earlier, there was a space in between the bars, and that's kind of the reason for this boundary concept here. And so you would say, this represents really the first class and the second class and the third class, etc. And every data value should fall into one of these bars because, again, that's why we did the 2 decimal places. All these data values are 1 decimal place, so it's not like we have to worry about a decimal, one of these data values kind of falling in the crack between 2 bars. And so that was kind of some of the reason for all that nonsense, but that's why we did it. And again, just keep adding 2, adding 2, adding 2, and you get all your boundaries. And we get all the way up to this last one, 75.95, which is well above where we said we wanted to go. We want to go 74.05, but that's fine. We had to do that because of the rounding we did. We rounded up to 2, which makes this a little bit more expanded out. But all our data values will fit here. And so what we do is we can then convert these into relative frequencies and say, all right, there's 100 data values, 59.95, 61.95. How many are in there? Well, here's all the data values that go up to 61.95, right? How many are there? There's 1, 2, 3, 4, 5. So 5 out of 100, that's our relative frequency for this first class. And that's why you get 0.05 as the relative frequency there. And then you go to the next one, 61.95 to 63.95. So you look at that, you go, boom, these 3 right here. Those 3 are the data values that fall into that next class. Well, 3 out of 100, right? 3 out of 100 would be 0.03, and we just keep doing that. How many would fall between 63.95 and 65.95? And count them up. And then turn it into a relative frequency. This does not have to be relative frequency in this vertical scale. This could just be pure frequency. Like, it doesn't have to be relative frequency. This could be 5 could be the height of this first one, and 3 could be the height of the second one, and 15 could be the height of the next one. This picture chose to use relative frequency here, but whether you use relative or regular frequency, this picture here, which is going to give you a shape of your data, is not going to change. Frequency polygons do a lot of the same thing. They're just a line chart instead of a bar chart, so it's still using the whole idea of the histogram and classifying your data values into groups. The way you identify a class, okay, a group of data, is not by a bar, but by a single point. And in order to do that, we typically would use the midpoint of a class. And that's found just by simply averaging your upper and lower bounds that we just found previously. And so, we would plot that as the data value, and then we would connect the bars, connect the lines to create this frequency polygon. Again, just a line chart. It's not that big a deal. So you see here would be the picture of what we just did, essentially. This would be for something else. This is for frequency distribution for calculus test scores. So if you looked at your boundaries that you created, the same way we created them in the previous example, and you want to find that first class goes from 49.5 to 59.5. So if you were doing a bar chart, you would have 49.5, you'd have 59.5, and you would have the bar here. And then the next one would be the next bar from 59.5 to 69.5, and so on. What you'll do is you have to identify this class here, not as a range of values, which is what it is, but by a single point. And the single point would be the midpoint of that class. So the way you find the midpoint is you take this data value, the lower bound, this data value, the upper bound, you average them. So add them together and divide by 2. Add those two together, divide by 2, you get the midpoint. That midpoint would then be the first class. And that one had a frequency of 5, so we put it there. The next one, the next midpoint is 64.5. There you go. The next one is here. And then once you have those, what you do is you connect the dots. But if you did that, it would just look like this. It would start here and would end here. So typically what you do with a frequency polygon is you kind of trail off the beginning and the end. A polygon is a figure where all the sides are straight lines. So this here would be a polygon. Okay? So to create the polygon, you have to finish it off, because otherwise your polygon will just look like this, and then it'll stop. You have to trail it off here, and now you got your polygon. Little silly stuff that is typical practice, but again, it's just visualizing your data. Okay? There's not a whole lot to this. It's just a way to understand what's happening with your data values. As a line chart versus a bar chart, how you do it doesn't matter. They all produce the same result. A picture that shows you this is the highest data value. This is where most of my, in this case, test scores are falling. I have less down this end, less down this end. Kind of has this shape to it. Whether it's a bar chart or a line chart, they're all giving you that. That's what you're looking for, the shape of your data. The next thing we want to do is to measure the location of our data. So that's pinpointing exactly where does a particular data value fall in reference to the entire data set. Is it in the lower end? Is it in the upper end? Is it right in the middle? And this will really start getting us into what really the next lesson for the following week, which is the idea of center and variation. But this is the start of it, is measuring the location of your data. So the best way you typically see this done is with percentiles and quartiles. And percentiles probably more so than quartiles. And once you get percentiles down, quartiles is just another version of that. And so it's basically how you divvy up your data. Quartiles divvy your data up into 4 separate groups, quarters. Okay, so 25% of your data in the first group. Okay, 25% falls in this first group. 25% falls into this next group, 25% falls into this next group, and then finally another 25%. Okay? So you divvy your data into 4 pieces, and each one falls into each group. This one that separates the first 25 from the second 25 would be Q1, quartile 1. This one would be quartile 2, and this one would be quartile 3. So if you were sitting at quartile 2, half of your data, 50% total, would be below it, and half, 50%, would be above it. Percentiles basically do the same thing, but break your data into 100 different pieces, okay? 100 different groups. And so if you were to lay your data values out in a string and cut them all up into 100 pieces, where 1% of your data fell into that piece, 1% of your data fell into that piece, etc., that's what percentiles do. And this would be P1, P2, P3, etc. So if you think about it, if I add up all these percents and I get all the way to P25, okay, P25 would have 25% of my data here, and then 75% of my data would be here. Well, that's the same thing as Q1. And then Q2 and P50 would be the same. And then Q3 and P75 would be the same. And so typically you hear about percentiles, like when you're talking about standardized test scores. You know, someone says, oh, my score was in the 90th percentile. Well, what that means is you were sitting at P90 with your score. That's the location of your score, your data value. And at P90, 90% is below it and 10% is above it. So if you said I'm in the 90th percentile in my score, that means 90% of people scored less than you and 10% of people scored more than you. So to calculate percentiles, there's a couple of ways we can do this, or quartiles, same thing. We can ask two questions. One is we can say which data value falls in the 90th percentile, or which exam score would be in the 90th percentile, or third quartile, or first quartile, or whatever. Or we could say, here is a data value. Here's a test score. I scored a 75. What percentile am I in? Okay. Two questions, kind of one is the reverse of the other. Well, let's start with the first one. I have a percentile. I'm looking for which data value would fall into that percentile. So I say, what score is the 90th percentile exam score for a given test? Okay. Well, there's a formula we can use, and this I formula is the one we're going to use here. In which case, there's a couple of things. One, you need to know the number of divisions. Percentile, the number of divisions would be 100. Okay. Quartile, the number of divisions would be 4, and that would go down there. So different formula depending on the number of divisions. Then there's this K. K is the percentile or quartile that you're looking for. Okay. So if I'm looking for the 90th percentile, this would be 90. If I'm looking for the second quartile, let's say, that would be 2. So that's how you would determine K. N, which is the other value in this formula, is the number of data values. Okay, number of data values. Those are all fairly easy things to find. And so then we can use this I to help us find what data value fits into a particular percentile or quartile. So here's an example. Listed are 29 ages of Academy Award-winning Best Actors in order from smallest to largest. It really benefits you if you put your data values in order to find out their location. So this is a pretty important thing. In this case, smallest to largest. You could do the opposite. You could do largest to smallest, but usually smallest to largest would be your best bet. It makes just your life a whole lot easier to calculate a lot of what we need to do here. And so let's say we wanted to find the 70th percentile. Let's find the 70th percentile. So in that case, K would be 70. N is the number of data values. They said there's 29 ages here. Okay? And the number of divisions, since we're talking about percentiles, is 100. So we're going to use this formula. We're going to say K is 70, N is 29. We're going to do this, and we're going to say, all right, we got 21. Now, 21 is not necessarily the answer. P21 is how we're going to identify the answer. So what this tells us to do is we need to look at a data value that's in the 21st position of the data set. So since this is in order, I can count 21 data values in, and I'll get all the way to 64, and that's the 21st data value, and therefore that is my 70th percentile. Okay? But the answer we got from this was a whole number. It's not always going to be. Let's look at the 83rd percentile. Well, everything's the same except for K is 83 now instead of 70. I plug all that into the same formula, 83, 100 divisions, 29 data values total. And you see the data value I get, the value I get out of I is 24.9. That's not an integer. So what are we going to do here? What we're going to do here is we're going to round this number down. And in this case, we're going to round it down to 24. We're also going to round it up, and we're going to get 25. So we have 24, and we have 25. Okay? So we're going to look at which data value is in the 24th position, and which data value is in the 25th position. And if we were going to count those out, they're going to end up being 71 and 72. And so what we're going to do here is we're going to say, all right, let's look at these two, 71 and 72. Which one of those is the 83rd percentile? Well, the answer is actually neither. The 83rd percentile is going to be the average of those two data values. So add those two data values together and divide by 2. You get 71.5. There's your 83rd percentile. Now you would say, well, that's not actually one of the ages listed. 71 is, 72 is, 71.5 is not. Why is that? Well, it's because, look at it, we have 100 different data values sitting, 29 different data values sitting in front of us. But we're trying to divvy this up into 100 pieces. That's what percentiles do. So there's going to be some pieces that fall in between data values, and that's exactly what happened here. And so that's why you have to do this whole song and dance about whether or not the I is an integer or not. If it's an integer, just count that many over, that's your answer. If it's not an integer, round down, round up, take the value that's 24th and 25th position, average them together, and that'll give you your percentile. Either way, I is not the answer to the question. I is going to help you locate the answer to the question. I oftentimes like to use L here instead of I to help me remember that this is a locator of the answer and not the answer itself. But, you know, I is really probably the more standard variable you see for this formula. But either way, this is a question where it says, okay, I have my data in front of me. Let me find what data value is sitting at the 70th percentile or the 83rd percentile. Same thing could be done with quartiles. You would just use 4 here instead of 100. You would do the same thing about, you know, whether the answer is a whole number or not and whether you have to round. But nonetheless, you know, this is it. You could also skip this altogether when it comes to quartiles and not go to a new formula where there's a 4 down here in the bottom. We know that P25 and Q1 are the same thing. P50 and Q2 are the same thing. And P75 and Q3 are the same thing. So rather than mess around with another formula and maybe think about trying to do it a totally different way, if I just said find Q1, I'm basically telling you to find P25. And so we could just use this exact same formula and find P25. So we'd do 25 over 100 times 29 plus 1. We would see what kind of answer we would get, whether that's a whole number or not, and then we would go from there. Well, you know what? Let's just do it. We're here in this problem. Let's do it. So we would get 25 over 100 is 1/4. So then 30 divided by 4 would give us 7.5. That's a decimal, right? It's not a whole number. So what are we going to do? We're going to round it down and up. Round it down to 7, round it up to 8. Okay, so we're looking at the 7th and the 8th value. 1, 2, 3, 4, 5, 6, 7, 8. So these two values right here, 29 and 30, we're going to average those two, and that'll be our answer. So Q1, which is P25, would be 29.5. Okay? So quartiles are just a version of percentiles when you think about it. Okay, so now let's say we want to do this in reverse. What if we wanted to figure out what percentile a particular data value falls into? So I take a test, I score 88, and I want to know what percentile that is for the entire class. And so we can do that by using this formula. So our formula here is this x plus 0.5y over n times 100. And we're going to round that one to the nearest whole number. So what does x, y, and n stand for? Well, n is the same n as we had previously. N would be the total number of data values that you have. Okay? X is the number of data values counting from the bottom of your data set up to but not including the data value that we're working with, that we're trying to find the percentile of. So this is, again, an important reason to have your data values listed in order. Okay, so it's easy to count this. Count how many data values are less than the data value you're talking about. And then Y is the number of data values equal to the data value that we're looking at. So sometimes you have repetition of values. So they'll say there are 5 people that scored an 88. That's what Y would represent, the number of values equal to the data value that we're working with. So that would be 5. Oftentimes, if there's no repetition, Y would just be 1. Okay? So we use all that, and that'll help us find the percentile for our particular data value. So let's go back to that Academy Award winning Best Actors ages, and they're arranged from smallest to largest. So we want to find the percentile for age 58. So find the percentile for the age 58. What percentile does that fall into? All right, so if we count from the bottom, 18, 21, 22, etc., count how many are strictly less than 58, but don't include 58 when you count. Okay? There are 18 data values that would fit that category. All right? 58 only occurs one time. So X would be 18, Y would be 1. There are 29 total data values, so N would be 29. So plug all that into your formula, and you would get 63.8. Round that to 64, and there you go. P64, the 64th percentile, is where 58 would fall. Okay? Now let's do this again. How about we find the percentile for age 25? So 25 is right there. What percentile would it be? It should be a fairly low percentile. You see it's in the beginning of the data set. So understanding how percentiles work, you should understand it's a pretty low percentile. Whereas 58 was 64th percentile. Okay? So about 2/3 of the way through the data set is where 58 fell. 25 is really close to the beginning, so we're going to expect a fairly small percentile for 25. So if we count, you clearly see 1, 2, 3. There's 3 data values that are less than it. So X would be 3. 25 only occurs one time, so Y would be 1. N is the number of values total, still 29. So put all that into your formula. You get 12.07. round that to 12. Yeah, you always round to the nearest integer, whether it's up or down based off your regular rounding rules. But the 12 would be where this rounds to. So that would be your 12th percentile. So P12 is where 25 falls. So pretty easy, okay, to calculate the particular percentile for a given data value. In terms of interpreting your percentiles, you don't really want to necessarily look at a percentile to be good or bad just simply because it's high or low. It's really relative to what you're talking about. What you really want to do is use the percentile as simply a locator for right now. So you understand like the 50th percentile is right in the middle. That's the same thing as Q2, the second quartile. So we call that the median. We'll talk more about that in the next lesson when we do center. But, you know, thinking about a high percentile is always good and a low percentile is bad. It's not necessarily the case. It really depends on what you're talking about, but just understanding what the percentile means. If I'm talking about P, say, 42, what that's telling me is that 42% of my data values are less than that, and 58% of my data values are greater than that. And this is sitting right here between the bottom 42 and the top 58%. So it's just a locator of where your data value falls. So that's really the important part about percentiles right now, is understanding what they're telling you. And they're basically telling you the location of a particular data value and how many or what percentage of values are less than it and what percentage of values are greater than it. So if you looked at, say, an example of a timed math test, okay, we talked about the first quartile for time it took to finish the exam was 35 minutes. So what could you interpret from that? Well, what I could say is that if Q1 is 35 minutes, so Q1 is 35 minutes, that tells me that 25% of my data values are less than that, and 75% of my data values are more than that. So that means 25% of the students finished in less than 35 minutes, and 75% of the students finished in more than 35 minutes. Is that good or bad? Well, no, it doesn't really matter necessarily. I would say, you know, if you had a low percentile, you know, it depends on how long you expected the test to take. But for me as a teacher, if students finish a test really quick, that usually tells me that maybe it was too easy, okay? And so if I was expecting them to finish in 35 minutes and only 25% did finish, then maybe that would be bad. If I expected them to finish in 2 hours and 25% were finishing in 35 minutes, maybe that would be good. I don't know. You can't necessarily take a good or a bad stance on some of this. It's just simply giving you information. Okay, one more example. At a community college, it was found that the 30th percentile of credit units that students are enrolled is 7 units. Okay, so here's P30. It's the 30th percentile. Okay, 30% are less than that, 70% are greater than that. And this is talking about 7 credits. Okay, so in terms of students registered for 7 credits, 30% of students have less than 7 credits in a given semester as their total number of credits. And 70% of students had more than 7 credits in a given semester. Is there a good or bad judgment there? Well, it depends on what you're looking for. If you're running a college, you would want students to enroll in as many credits as possible. Typically, we think of full-time as 12 credits or more. And so if you're looking for a lot of full-time students, you would probably want more students to be enrolled in 12 credits or more. And this is a pretty high number, over 7 credits, 70%. So that might be closer to what you're looking for. If you're running a community college, there's a lot of students, a large number of students who are part-time students who would register in less than 12 credits. So 7 credits would seem about right. It's about 2 classes. And so maybe you're looking at saying, well, what's our part-time versus full-time enrollment? But it's, again, still not necessarily good or bad, I mean, unless you're looking for something very specific, but it's just giving you information as to how many students you have in certain parts of the enrollment patterns. But really, again, it's just giving you information about what's happening with your data set. And I think that's the most important thing you need to get out of these percentiles.